Okay, we're in section 4 on the examples now. The examples come in 3 parts. One is simplifications, identities, and then equations. They're certainly all related. I'll work through all the examples, and hopefully, after paying attention to these examples, you're able to do them on your own. So let me go for another share. And we'll do number 1. All right. So the first thing I want to point out to you is we have these square problems over here, and they're squaring the cosine, squaring the sine. And the angle is 30 degrees. So let me put my reference triangle down for you. No, this does not need to be done. If you know, for example, what the cosine of 30 degrees is and sine of 30 degrees is, that's fine. Certainly, these are simple triangles. And now we know what we have to do. So I have to do the cosine of 30 degrees and square it. And I have to do the sine of 30 degrees and square it. The cosine of 30 degrees is root 3 over 2. And the sine of 30 degrees is 1 over 2. All right, I got to do the arithmetic now. This can be 3/4 minus 1/4. That would be 2/4 or 1/2. All right, there's also sage code here. I do recommend you start looking at that sage code and playing around with it. You're not going to be testing on that though, but you should start thinking about moving forward. All right, let's go to number 2. And number 2 is, a simplification problem. And I want to try to simplify that. And what am I seeing? Sine theta times the secant. My recommendation is write the secant as 1 over cosine of theta. Well, sine theta over cosine theta. You should recognize that as being the tangent of theta. That's the simplest way we could write that down. All right. There's also code over here. If you want to look at the sage code, please feel free to do so. All right, let me do number 3 now. And what I'm seeing, what appears to be a Pythagorean identity. I want to review those with you. I push this over. I'm just going to review the Pythagorean identities. So the first one we introduced to you was a sine squared theta plus 1. Plus cosine squared theta, equals 1. And then we divide it through by, for example, cosine squared. We would get tangent squared plus 1 equals secant squared theta. The other one we did was we have to do it by sine squared. We'd get 1 plus cosecant. Whoops, I did it again. And that's part of me daydreaming, actually. Cosine divided by sine is going to be cotangent squared theta. And if I'm dividing that by sine squared, I get cosecant squared theta. All right, so which one are you looking at over here? I want to point out, I'm looking at this one over here. And I want to point out, if I'm looking at this one over here and I solve for tangent squared, what would you get? Secant squared theta minus 1. So now I'm ready to simplify this guy. And the simplification of it would just simply be, the top would be just tangent squared over sine squared. All right, my recommendation is to rewrite the tangent in terms of sines and cosines. So tangent squared would be sine squared over cosine squared. And the bottom is just simply sine squared. It's already there. What do I see now? Cancellations. And what am I left off with? I'm left off with 1 over cosine squared theta. And you should recognize that as being the secant squared theta. I just want to point out, if you're looking at the answer key, you'll see these answers. You also see some sage code over here. I think it's important you start looking at the sage code and playing around with it. All right, let's go to number 4. And my goal here is to simplify. That's what I asked me to do. All right, number 4 down for you. And I got sine squared x times cosecant squared x minus 1. Well, what I'm going to do over here is I'm just going to write the cosecant squared in terms of signs. What would that be? 1 over sine squared x minus 1. Then I'd simply multiply it out. What do you get? You get sine squared over sine squared, which would be 1 minus sine squared x. You should be becoming more familiar with the Pythagorean identities, and you should recognize that now as being the cosine squared of x. That's the simplest way I could write that down. I do want to point out, if you're looking at the notes, which we want you to look at, you would see that answer right over here. All right, let's do the next one. This is going to be number 5 now. Number 5 is a cofunction identity. And the sine of pi over 2 minus x is actually the cosine of x. And the cosine of pi over 2 minus x is actually the sine of x. You should recognize that cosine over sine is the cotangent of x. That's the simplest way I could write that one down. Of course, that answer is listed for you. All right, let's talk about the next one, number 6. And number 6 looks more difficult. All right, so I'm going to write it down for you. Cosine of a over 1 minus sine of a. And I'm going to write the tangent in terms of sines and cosines. So that would be, give me 1 second. That would be sine of a over the cosine of a. All right. So what I'm going to do now is, and again, there's a variety of things you could do. I'm going to do something what some people say is very strange to do that, but at one point you need to start trying things. And I'm looking at the bottom. I could get a common denominator, for example. But what I'm going to do is I'm going to multiply the bottom by its conjugate. And what's conjugate of 1 minus sine a? That would be 1 plus sine a. Now remember this, if you multiply the bottom by 1 plus sine a, you must multiply the top by 1 plus sine a. I also want to recommend these problems are written to work. What I mean by that, they're going to work out really nicely if you move forward. Now, the top is going to be cosine of a times 1 plus sine a. No, I'm not multiplying that out. I'm actually multiply the bottom out. It would give me 1 minus, these are conjugates, sine squared a. Yeah, I know it's work. Let's keep moving forward. And this is cosine of a times 1 plus sine a. And the bottom is cosine squared a, Pythagorean identity. There's a cancellation of a cosine, and you're left with 1 plus sine a. And you're left with 1 factor of cosine a in the bottom. All right, let's keep going. I'm going to add these two fractions together. The common denominator is cosine a, and you would get 1 plus sine a minus sine a, which is 1. What do you get over here? Well, you should recognize that 1 over cosine a is a secant of a. All right, so I want to go back and talk about looking back at the original. And give me 1 second. I'm looking at number 6, and they say it's secant of a, as we expected. All right, I'm going to do number 7. And, looking at it, it doesn't look that bad. I'm going to write it down for you. This is 7 now. And I'm going to make an attempt to factor the top. And the top would factor the cosecant. Oops. Let me just clean that up a little bit. It doesn't look right. Cosecant x minus 1 cosecant x plus 1. And the bottom factored is cosecant x minus 1. What's nice about this? There is a cancellation. And what he left off with, something pretty simple. Cosecant x plus 1. All right, go to the next page. I do want to point out next page, you do see the answer over there. All right, I'm going to do number 8 now. And I'm going to pull this aside. Let's do number 8. The first thing I do in number 8 is I realize some students have trouble with fractions. Is I would just simply factor out the fraction on each of those factors. And the first factor, a common factor, would be 1/3. And then what do you get? Tan x plus secant x On the second factor, there's a common factor of 2/3. And what are you left off with? Tan x minus secant x. All right, I'm going to move things around. It's called the commutations multiplication problem. And I'm going to associate. So I'm going to associate the 1/3 with the 2/3, and that would give you 2/9. And now I'm going to do the multiplication. And you would get tangent squared minus tan x secant x. Let's see what we get. Plus tan x secant x minus secant squared x. All right, let's keep moving forward. This is 2/9. And what do you see now? Tangent squared x. I want to point out these two middle terms disappeared. And then you get minus secant squared x. All right, now someone says I'm done now. You could be. I want to point they look like it might be related to a Pythagorean identity. So let me write that down for you. Sine squared theta plus cosine squared theta equals 1. If you divide through by the cosine squared, you would get tangent squared theta plus 1 equals secant squared theta. Well, I think I'm seeing it now. Tangent squared theta minus secant squared theta would equal minus 1. I think I'm ready. This is going to be 2/9, and tangent squared x minus secant squared x is just simply minus 1. What does this give me? Minus 2/9. Again, I want to point out to you, look back at the answer to make sure they have that listed for you. And they do. All right, I'm going to do number 9 now. And number 9 is a substitution problem. All right, so what do you have over there? They want you to substitute in x equals 2 cosine theta into this expression over here and simplify it. See if we can do that. Well, the first thing I notice is that there's an x squared in the problem. So x squared would equal 4 cosine squared theta. I'll jot that down. 64 minus 16 times 4 cosine squared theta. And keep simplifying. 64. 16 times 4 is 64 cosine squared theta. Keep moving. And what do you get here? Well, common factor would be 64. And then you get 1 minus cosine squared theta. Well, I recognize that as being the sine squared. It's a Pythagorean identity. Here comes the part where students get confused. The square root of 64 is 8. And the square root of sine squared is actually the absolute value of the sine of theta. However, they were kind of kind to me. What did they tell me? The angle is between 0 and pi over 2. So if the angle is between 0 and pi over 2, it's over here, the sign would be positive. Therefore, I can remove the absolute value symbol. All right, that's simplification. Again, if you look at it, you would see the answer right there. All right, let's look at number 10. And number 10 is, again, a simplification problem, but again, that might be something very difficult, particularly if you try to evaluate the cosine of 49 degrees. It would be very difficult to do. I'm not saying impossible, but difficult to do. So what I'm going to do is I'm going to look for cofunction identities. And what I notice is that the cosine, I'll write this over here, of 49 degrees is the same thing as the sine of 90 degrees minus 49 degrees, which would be the sine of 41 degrees. That's one thing I noticed. The other thing I noticed is a cosine of 83 degrees is the same thing as a sine of 90 degrees minus 83 degrees, which is going to be sine of 7 degrees. All right? So I'm going to look at this one here. This is number 10. And it gives the cofunction identities. And what do I say? Well, the cosine squared of 49 degrees is the same thing as sine squared of 49 degrees. Plus, the cosine squared of 83 degrees is the same thing as a sine squared of 7 degrees. Then what do I say? Plus cosine squared 7 degrees plus cosine squared 41 degrees. Now, what do I notice now? This is a Pythagorean identity. It's 1. And this is a Pythagorean identity. It's also 1. So what do I get over here? 1 plus 1, which is 2. Right? The answer is listed over there. Let's go to the next question. And it's number 11. And number 11 is a substitution problem again. Looks fairly simple. And what do you get there? Well, I think I can probably just one a little quicker, just one similar to it. I noticed some information down there that might confuse you, but right now, what's a squared? I don't know, but I'll put down a squared. And what's u squared? Well, looking at it, it's a squared cosine squared of u. I'm sorry, theta. Well, I'm sorry. Got u in my mind. I'm not going to do what I did in the past, which is factor it. That's a squared times 1 minus cosine squared theta. What would this give me? Well, looking at it, 1 minus cosine squared, it's Pythagorean identity. That's a squared times sine squared. The square root of that, fairly simple, it's going to be the absolute value of a times sine theta. That's something in math 119. Here's the deal, though. They told me a is a positive number, and the angle is between 0 and pi over 2. So a is positive, and the sine of theta would be positive. So the absolute value of that would be a sine theta. Put a box in that. Look at the answer key, and you'll see that there. All right, let's do number 12. And 12 is a simplification problem. My gut feeling is if I write things in terms of sines and cosines, things may work out pretty nicely. So it's cosine theta plus, now tangent theta is sine theta over cosine theta times sine theta. I'm going to keep rewriting it. This thing is cosine theta plus sine squared now, theta over cosine theta. Well, I want to get a common denominator, cosine theta. And then what do you get in top? You would get cosine squared theta plus sine squared theta, which we know is a Pythagorean identity is 1. So it's 1 over cosine theta. What's that? Secant theta. Look at the k. You'll see that in the k. All right. Let's look at number 13. And number 13, again, for some students, they look and say, oh, it's really difficult. And I want to really kind of encourage you, we don't give you difficult problems, we give you problems that you can do if you try. Let's write this down, sine theta. And I get cosine theta plus cosine theta and 1 plus sine theta. Well, let's try something a little different this time. I'm going to, look at the problem and see if I can maybe work on it and get a common denominator. It looks pretty simple to do. And that would be cosine theta. And I get 1 plus sine theta. And this would be sine theta times 1 plus sine theta plus, well, cosine theta times cosine theta is cosine squared theta. All right, what do you get over here? Sine theta, right, plus sine squared theta plus cosine squared theta. What do you get in the bottom? Cosine theta, 1 plus sine theta. Well, I'm seeing a Pythagorean identity on top, and that's 1. So what do I get? Sine theta plus 1, and on bottom I get cosine theta times 1 plus sine theta. Well, I now know there's a factor in top and the bottom that are identical, and they would cancel off. And what would be left off with? 1 over cosine theta, which we know is the secant of theta. All right. Again, I want to point out, you look at the answer key, you'll see that as well. All right, let's look at number 14. Number 14, I would recommend just to simply factor it, looking at it, that's the Greek letter beta, by the way. I'm going to say what's common between those two is cosine of beta times cosine squared beta plus sine squared beta. And it's Pythagorean identity, so this is going to be cosine of beta. Fairly simple. Let's go to the next page. Again, we see that there in the answer key. Let's do number 15. And certainly want to encourage you to work on these problems, but more importantly, to do them independently of me. All right, but here's the deal, 15. And I'm going to write it as two terms. Secant, that's a Greek letter alpha, over the tangent of alpha minus cosine of alpha over the tangent of alpha. I'm going to keep rewriting it. Now I realize the secant is 1 over cosine, and the tangent is going to be sine over cosine. It's going to probably simplify a little quicker than a lot of students can do it, but that should be written there eventually. Minus, let's go to the next term. This would be cosine alpha, sine alpha, cosine alpha. All right, let's take a look at it. And what do I notice immediately? Some cancellations in the problem. And I'll tell you what those cancellations are. The cosine of alpha cancels here. And what do we get? I guess something pretty simple. I'm going to write it down for you now. You get a common denominator now with sine alpha. And on top you get 1 minus cosine squared alpha. Now what's 1 minus cosine squared alpha is sine squared. On bottom we get sine of alpha. One of the signs cancel, left off with sine of alpha. All right, let's go back, look at it. And what are you seeing? You're seeing that there. All right, let's go to number 16, a little more complicated. Write it over here. And what do you see there? Cosecant. I'm going to write that as 1 over sine. The cotangent, that's going to be cosine over sine. The bottom is 1 over cosine minus 1. Again, I'm just doing things, a little differently each time, but for the most part, you got to develop a style yourself. And someone says, well, I don't like what you're doing. I want to do something different. We want to encourage it. Do something different. So I can multiply top and bottom by sine x cosine x. Sine x cosine x. All right. What do you get there? Let's see. First term would give me cosine x. The second term would give me cosine squared. Let's do the bottom. What do you get? Sine x minus sine x cosine x. Now I'm going to factor top and the bottom and see what we get. Cosine x, 1 minus cosine x. What do you get in bottom? Sine x, 1 minus cosine x. Well, lo and behold, common factor cancels off, and we left off with cosine over sine, and cosine over sine is the cotangent. Again, I can't say enough times, look at the key, make sure you're staring at that. All right, next section is going to be the identities. And I want to point out about identities, it's really simplifications, but here's what they give you. They give you what the simplification is. So what you need to do is choose the side that simplifies to that. So number 1, again, we're in the identities now, is cosine theta times secant theta minus cosine theta equals sine squared theta. So what we're doing is we're choosing a side here. Someone says, what side are you going to choose? Well, I'm going to emphasize that you choose a side that allows opportunity for simplification. I'm going to choose this side here. What I'm going to do with that side, I'm going to work on it until it looks like the other side. So let's go one step at a time. So I'm going to write things in terms of sines and cosine. Cosine of theta, this would be 1 over cosine theta minus cosine theta. Well, that's done. Let's keep going. Multiply it out. What do you get? 1 minus cosine squared theta. And I recognize that to be the sine squared theta, which is exactly what we want to show QED. Let's go to the next page. And again, I'm looking at this number 2 now. And with number 2, what you're doing is you're looking at the problem. I'll write this down for you. And I'm looking at it. I see 2 tan secant equals 1 over 1 minus sine x minus 1 over 1 plus sine x. Again, my goal here is to choose a side, rewrite that side so it looks like the other. I'm going to say this side looks like it has some opportunity for rewriting it. So let's start rewriting it. One step at a time, common denominator, 1 minus sine x, 1 plus sine x, 1 plus sine x, minus 1. Now minus a minus would be plus sine x. Let's keep moving. What do you get on top? 2 sine x. What do you get on bottom? Well, pretty simple multiplication. It would be 1 minus sine squared. Let's keep moving. I'm not there yet. I'm seeing 2 sine x. On bottom is cosine squared, which means cosine x times cosine x. This simplifies to 2. Sine over cosine is tangent, and 1 over cosine is secant. QED. All right, let's go to the next one. Number 3, let's take a look at it. And what do you see there? You see cosine of u and 1 minus sine of u, and u equals secant of u plus tan of u. Now I'm going to choose a side. So this is what side you're going to choose. Well, you choose a side that you would like to work with. I want to work with the left side now. Put it to work. And what I'm going to do is I'm going to rewrite this guy. I'm going to multiply top and bottom by the conjugate. Remember this, if things are not working out, erase and try again. What do you get over here? Well, the bottom is 1 minus sine squared now. And the top is cosine of u times 1 plus the sine of u. Now let me keep looking at it. I'm looking at the bottom. I notice it's cosine squared now. You know what? I noticed I wrote a theta down there. I got my eraser out. This happens to me sometimes. I'm not looking at the letters. And I'm so used to writing theta down that I continue to do that. Simplification again. Cosine u. And we're left on top 1 plus sine u. I'm going to split into 2 terms now. And those 2 terms would be 1 over cosine u plus sine u over cosine u. And what do you get there? Secant u plus sine over cosine is tangent of u. They may not realize this, but this is what you were supposed to show. You were supposed to show this over here. And we did that. We got secant u plus tan u. All right, fairly simple. All right, let's do number 4 now. And again, I'm looking at number 4. And number 4, I see the Greek letter delta. And I've got to pick a side. So let me write this down. So I'm going to say 1 plus cosine delta cosine delta is tangent squared delta over secant delta minus 1. Right. So this is what side you're going to pick. I'm going to pick the right side. And I'm going to work with that side until I figure out what it is. All right. Now, I'm hoping that this thing simplifies quickly, but sometimes they don't. Sometimes it takes a long time to get there. You take a wrong path. You can always erase and try again. So I'm looking at it. I'm going to write in terms of, I don't know. I'm going to multiply the bottom. I'll multiply by the conjugate. Put this down. So what's going to be secant delta plus 1 secant delta plus 1. You know what? I don't want to do that. I'm going to try something different. There's one encouraging. Try things. Look at it and say, it looks too much work. I'm going to write in terms of sines and cosines instead. Let me put that down for you. Sine squared delta, right, over cosine, I made my fraction bar a little too long there. Sorry about that. Cosine squared delta over 1 minus cosine delta minus 1. And so what are we going to do now? I'm going to multiply top and bottom by cosine squared delta. Cosine squared delta. All right, let's keep going. And I'll put this over here. The bottom looks pretty easy to do. It's going to be cosine delta minus cosine squared delta. Don't be discouraged. It's going to work out. Top is sine squared delta. Now, by the way, I'm not there yet, but I'm going to keep rewriting it until I get there. When you get over here, I'm going to factor out cosine delta on the bottom. And we left off with 1 minus cosine delta. On top, I recognize sine squared to be 1 minus cosine squared delta. I notice the top is factorable to 1 minus cosine delta times 1 plus cosine delta. Bottom is cosine delta, times 1 minus cosine delta. Something cancels off here, and we left off with something pretty simple. You're left off with 1 plus cosine delta over cosine delta. By the way, that's what we wanted to show. We got this right over here. Again, Q, A, D. All right, let's go to the last one. Not the last one on this page over here, which is number 5. All right, again, if you look and say, I don't think I can do that. It's too difficult. It's got to work, right? It really has to work. So I'm looking at number 5. And the first thing I would do is just start rewriting it. And I'd pick the left side. So I'm going to circle it for you. And if you did that, let's write that down for you. Again, I'm picking the side. And what do you get there? Common denominator. All right, here comes the tough part. Cosine x minus cosine y times cosine x plus cosine y plus sine x minus sine y. Wow, this is going to go on forever, isn't it? Put a line over here. Times sine x plus sine y. Now I want to pay it. My hope is really the top turns out to be 0, but who knows? Maybe they wrote a bad problem. Put the bottom down for you. And what do you get there? Well, this guy's pretty easy to do, actually. And what are you going to get there? You're going to get cosine squared x. The two middle terms would disappear, by the way, and then you get minus cosine squared y. Plus, the second guy is also pretty easy to do. You get sine squared x. Two middle terms would disappear. Then you get minus sine squared y. Well, I'm starting to realize now I've got a Pythagorean identity here. I want to put out what I'm looking at. I'm looking at this and this. And that would add together to be 1. I'm also looking at this and this. And if you factor out minus 1 from that, you'd have another Pythagorean identity. So that would be minus 1. What do you get in bottom? Really doesn't much matter now. But I want to point out to you, I'm going to write that down for you. And that's going to be sine x. Let me go back to black ink. Sine x plus sine y. Cosine x plus cosine y. It's going to be 0, right? Do we want to show that? Of course we did. They said it was 0. We did that. QED again. Let's go to the next page. And next page, we got number 6 now. And I pull this on the side. And what I'm going to do there is I'm going to, pick a side. And so this is what side you're going to pick. I'm going to pick the right side. I'm going to start rewriting it. What do you get over there? Sine x. And I'm going to factor that guy. What would that be? 1 minus cosine squared x. That's a factorization of that. All right. You can multiply that if you want. What does this give us? Go to the next stage. Sine x times sine squared x, Pythagorean identity squared. What does that give me? Well, I got 5 factors now. Exactly what we wanted to show. QED. All right, let's go to number 7. 7, they're using the Greek letter epsilon. And I got to pick a side. So what side are you going to pick? I'm going to pick, this looks like a very familiar problem, by the way, doesn't it? I'm going to pick the left side. I'm going to start rewriting it. All right. So sine epsilon and 1 minus cosine epsilon. I can multiply the top by its conjugate, of the bottom, by the way, 1 plus cosine epsilon. Now remember, if you multiply the bottom by that, multiply the top by that, what do you get here? Sine epsilon times 1 plus cosine epsilon. The bottom would be 1 minus cosine squared epsilon. What does that give me? Sine epsilon, 1 plus cosine epsilon. The bottom is just simply sine squared now, Pythagorean identity. This reduces. What does it reduce to? The sign cancels. 1 plus cosine epsilon over sine epsilon. What do we get? What we want to get, again, a QED. We show what we want to show. All right, let's go to the next thing. And when I do these problems over here, I want to point out we do provide good pictures for you, but right now I'm just going to just do my, a sloppy picture of it. And we have 3 models to follow. One is the cosine of an angle equals a number, sine of an angle equals a number, or the tan of an angle equals a number. And I'm seeing it. Cosine of an angle equals a number. I would draw a picture of the cosine curve. Looks like this. It's a rough picture. Don't be great. I know what these values are. For example, this is 90 degrees. This is 180 degrees. That's 270 and 360. I'm going to look at the ratio, and that's 1 over minus 1 over root 2. And that would hit here, and it would hit here. So I know the first one hits between 90 and 180. I don't know what the number is yet. And the next one is between 180 and 270. I want to get a reference triangle. And the reference triangle I'm going to put down is a 45. And why is that? Because it's raised to the number 1 over root 2. 45 degrees, 1 root 2. So I know my reference. I'll put this over here. Theta reference is 45 degrees. My first angle is between 90 and 180. And if it's between 90 and 180 as reference of 45 degrees, the angle X would be 135 degrees. Now the next one's going to be between 180 and 270, but as a reference of 45, that means it's 225 degrees. All right, go to the key, make sure you're seeing those 2 numbers, and the 2 numbers that you're seeing over here, right there. I do provide a better picture for you. But again, it's your mileage. You may say, I don't like your pictures. I want to do my own pictures. I'm certainly going to do my own pictures as well. So let me go to number 2 and see if I can do it. Again, it fits the model. And what's that model? You know, the sine of an angle equals a number. So what I'm going to do, draw my picture. And when I put a picture down, it's a rough picture, but the sine function, I just put one cycle down, looks like this. And it says minus root 3 over 2. And you should have an idea what that number is now. And that number, before I do that, I know that's 0, that's 90, that's 180, that's 270, that's 360. So I put my, the ratio minus its negative number, hits it there, hits it there. So the first one hits between 180 and 270, and the second one hits between 270 and 360. What am I doing? I'm looking for a reference triangle. So I'll put the reference triangle down for you. I'm going to say it looks sort of like this over here. That's going to be root 3, 2, 1, and you should recognize that to be 60. So the reference angle is 60 degrees. But my angle is between 180 and 270. It has a reference of 60. So x must be 240 degrees. The next one is going to be between 270 and 360, but has a reference of 60. So it's going to be 300 degrees. I want to point out these answers right over here. We do provide a better picture for you as well, by the way. All right, the third one is a tangent problem. And what am I going to do is going to draw a picture of a tangent. All right, so I'm going to do. And what does a tangent function look like to me? Well, that's pretty simple. I got asymptotes at, minus 90 and 90. And I got the picture looks sort of like this over here. All right, so what do they want? They want the tangent to be the number 1. So I'm going to put that line in, and it hits it. And where does it hit? It hits it between 0 and 90 degrees. So I'm going to say it's pretty easy. It's a 45-degree reference triangle, right? So what's x going to be equal to? 45 degrees. Here's where things get interesting now. Whoops. Let me just get my eraser out. This keeps going and going and going. What do I mean by that? The next tangent would look like this over here. Now, what I know about that is that the tangent has a cycle length of 180 degrees. In other words, the distance between these things is 180. So that means the next solution up is 180 degrees away. So what's 180 degrees from 45? Well, 180 plus 45 is 225 degrees. But you can keep doing this all day long, but I just got to do the ones between 0 and 360. Now, if I add 180 onto that number, I'm beyond 360. Okay, let's go to the next one. Pictures. We're going to number 4 now. And 4 is the secant, and that does not fit my model. So the first thing I would do in number 4 is I would write it so it fits my model. And my model is, this is related to cosine. So the cosine of x would be minus 1 over root 2. It's the reciprocal function. Draw the picture of the cosine function. It should be pretty easy to do that. Doesn't have to be a great picture. Something like this over here. Again, I know the numbers, 90, 180, 270, 360. My ratio, minus 1 over root 2, bop, 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 hits it there, hits it there. Getting a little better at this. I know my first angle is between 90 and 180, and the second angle is between 180 and 270. Just look at my picture, right? So what's the reference? The reference is 45 degrees. Let me write that down for you. The reference is 45 degrees. Right, let's write x down. What's x going to be equal to? Well, the first one's between 90 and 180 has a reference of 45, which means it's 135 degrees. All right. The next one, if I look at it, is between 180 and 270 has a reference of 45 to 225 degrees. Now, someone's going to say, I'm looking at this thing, and they didn't talk about degrees. They talked about the radian measure. All right. So let's write the radian down now. X is 135 degrees. If you have to multiply it by the conversion factor, which is pi over 180. And if you simplify that, the degrees will cancel off. And what would you get? 3 pi over 4. The next one is 225 degrees. Again, if you need to, multiply the conversion factor. And this would turn out to be 5 pi over 4. All right, let's go to the next one. And again, next one, number 5, does not fit my model. Why is that? It's cosecant. So I'm going to write it as sine. The sine of x is going to be the root 3 over 2. My goal here is to draw the picture. The picture should be quite simple to do. Looks like this over here. I know the numbers, 0, 90, 180, 270, 360. I'm looking for the ratio root 3 over 2. It's there. It's there. I know the reference for that. That's a 60-degree reference. I'll write that down for you. What's the first number going to be? X is between 0 and 90 with the reference of 60. So it's 60 degrees. What's the second one going to be? It's between 90 and 180 with a reference of 60, 120 degrees. Remember, they didn't speak degrees. They spoke in radian. So I got to convert that. And again, if you need to put the conversion factor, that's fine. It should be pretty easy to do. Pi over 3. And this one's going to be 2 pi over 3. Again, look at the key, and you'll see that in the key as well. All right, let's go to number 6. And number 6 is, really doesn't look bad, but they got something strange here. They say n as an integer constant. Put number 6 down. And the sine function looks like this. That'd be a great picture. I know the numbers, 0, 90 degrees, 180 degrees, 270, and 360. I'm looking for the ratio, and the ratio is minus 1 over root 2. There and there. I know the reference for that. The reference is going to be theta reference is going to be 45 degrees. Let's write this down. X is, well, the first one occurs between 180 and 270 with a reference of 45. So it's going to be 225 degrees. The next one is going to occur between 270 and 360 with a reference of 45, which is going to be 315 degrees. All right. Here's where they said something strange, though. They said n is an integer constant. Well, what I want to write down is that this keeps repeating itself on the cycle length. And what's the cycle length? 360 degrees. So plus 360 degrees n plus 360 degrees n, with the understanding that n is an integer value. All right. I'm going to write a little bit differently. And the reason for that is we would like to speak in radians. All right. So you should be able to convert 225 to radian by now. And that would be 5 pi over 4. And 360 degrees in radian is 2 pi n. What's 315? Let's see, 2, 4, 6, 7 pi over 4 plus 2 pi n. All right, what I'm going to encourage you over here is look at the k, and you should see those answers in the k. All right, there's also a picture provided for you. All right, number 7, I'm looking at it, again, that integer constant thing, it's not bothering me so much anymore. I want to point out what bothers me about this not written in the form I want. So my first goal is to write in that form. And I'm going to write it as cosine x equals 1 over root 2. Right? First step, draw the picture of the cosine. Looks sort of like this over here. I know the values, and again, it's kind of rough, but that's 9. I'm sorry, this is 0, then 90, and then 180, 270, 360. Find the ratio, 1 over root 2, hits it there, and hits it there. So the first time it hit between 0 and 90, and the second time it hit between 270 and 360. I think you can write this down. X would be equal to, well, the reference is 45, and between 0 and 90, if it's 45, it's 45 degrees. Remember, it repeats on its cycle length, which is 360 degrees. So I'm going to write that down, 360 degrees n, with the understanding that n is an integer. All right, let's put the next one down, x equals. Well, the next one occurs between 270 and 360, which can be 315 degrees, plus its repetitious pattern, 360 degrees n. Let's put the radian measure down, pi over 4, plus 2 pi n, and this would be what? 7 pi over 4, plus 2 pi n. All right, go to the next page, and you'll see those answers listed for you. All right, let's go to number 8. And number 8, I guess tangent equals root 3, and this n is integer constant. I'm going to draw my picture. And again, you don't have to draw a picture. I'll point out for a lot of students, drawing a picture may or may not be helpful. You have to determine that by trying. Look for my ratio, which is root 3. Hits it there. Question is, what angle would that be? I'll write the reference down for you. Theta r. The reference for that would be, when we give you root 3, the ratio for tangent, that would be 60 degrees. All right, here's the deal. What's the cycle length? What's the cycle length here? Well, if you thought about it, it goes from minus 90 to 90, it's 180 degrees. It keeps repeating itself every 180 degrees. So let's write this down, x equals 60 degrees plus 180 degrees n, understanding that n is some integer value. Let's put the radian down for that. 60 would be pi over 3. 180 degrees is pi. All right, look at the key. I'm seeing it here. They also gave me a picture, by the way. Well, let's do number 9. Again, somebody look at this and say, why you give me something with a square in it? I don't understand that. Well, you do, because you've been doing this since Math 100. I need to rewrite it, and this would be 4 cosine squared x equals 2. Divide both sides by 4. And what do you get? 1/2. And then I use square root rule, and I get cosine x. Here comes the tricky part, plus or minus 1 over root 2. What am I going to do? Cosine curve looks like this. All right. And again, I'm familiar with the numbers. That's 0 degrees, 90 degrees, 180, 270, and 360. And now find the ratios. 1 over root 2 hits it here and there. And minus 1 over 2 there and there. Question is, what's the reference triangle? Well, the reference angle would be 45 degrees. So this should be very easy to write down now. The first one occurs between 0 and 90 with a reference of 45. Keeps repeating itself on the cycle length, which is 360 degrees, n, with the understanding that n is an integer value. What's the next one? It's between 90 and 180 with a reference of 45, which means it's going to be 135 degrees plus 360 degrees n. What's the next one going to be? It's between 180 and 270 with a reference of 45, 225 degrees plus 360 degrees n. What's the next one going to be? Well, it's between 270 and 360 with a reference of 45, so 315 degrees plus 360 degrees n. Well, I'm going to write this down now in the radian, which is pi over 4 plus 2 pi n. This is going to be, let's see, 3 pi over 4 plus 2 pi n. And this is going to be, let's see, 5 pi over 4 plus 2 pi n. And this one's going to be 7 pi over 4 plus 2 pi n. This is a great answer. However, I want to point out one of the goals in life is to simplify things. So I'm going to write down the numbers for you. And as a pattern, 45 degrees, 135 degrees, 225 degrees, and 315 degrees. You may notice that these things are going up by 90 degrees. So it's a really easy way to write this problem down is x equals 45 degrees plus 90 degrees n, or pi over 4 plus, well, what's 90 degrees? Pi over 2. This is the easiest way to write the answer down. However, this one is fine. This one is perfect, though. All right, both, in my opinion, get full credit. Now let's go to the next page. And I'm seeing that right here, my compact answer, and I'm seeing these answers over here as well. All right, let's go to number 10. And again, looking at it, you might say to yourself, I can't do that. Of course you can. We don't give you problems you can't do. So in number 10, I'd say the first thing to do is probably try to factor it. I'll put that down for you. So 2 sine x minus 1. We'll check it, by the way. Plus 1. Let's see if that works. I get 2 sine squared. Yeah. Minus 2 plus 1 is minus 1. Well, that's pretty good. All right. Let's write this down. Zero product rule. So this becomes 0 when the sine of x equals minus 1/2. And this becomes 0 when the sine of x is equal to 1. Well, same thing. I'm going to draw the picture. And the picture, look over here, sine function. Look for the ratio. Before I do, I want to make sure I'm, what I'm doing, 0, 90, 180, 270, 360. Hits it here. Boy, that was easy. What's x there? X is 90 degrees. Does it repeat itself? Every 360 degrees n. with the understanding that n is an integer value. Right, let's do this one over here. Again, same story. I draw a picture of the sine function. And I want to point out, 0, 90, 180, 270, 360. My ratio is minus 1/2. Hits it there. And what does that mean? Hits it between 180 and 270, and 270 and 360. I got to do the reference now. And what's the reference going to be? Well, the reference is 30. All right, let's write it down now. What's x going to be? Well, it's between 180 and 270 with a reference of 30, which makes it 210 degrees plus 360 degrees n. X is, now the next one's between 270 and 360 with a reference of 30, which is 330 degrees plus 360 degrees n. I'm going to write down in the radian measure, and I'm going to do one thing at a time. And 90 degrees is pi over 2 plus 2 pi n. 210 degrees, well, that's going to be 30 degrees, right? It's 7 times 30 degrees, and that's going to be pi over 6. So 7 pi over 6 plus 2 pi n. And the next one is 330, and that's 11 times pi over 6, so 11 pi over 6. Again, I want to encourage you to look at the answer key to make sure you're staring at those answers, and you are. By the way, they may simplify them. I'm not too concerned about simplifications, all right? Okay, so this covers that section out, and you got supplemental activities. I realize this goes very quickly for some students. You want to study the material and then get busy with the supplemental activities. Thank you.